By modern definitions, air pollution includes greenhouse gases, to the point where they seem to be the only kind of air pollution that most people even know about. But air pollution also includes all sorts of other air contaminants, which may be poisonous or toxic or carcinogenic, or may just be otherwise unpleasant or nasty. And this is the kind of air pollution that I'm going to be talking about in this video. Some air pollution is created by nature, while some is created by humans. Some of the human-made air pollution is produced by combustion activities, while some of it is produced by things like farts and agriculture. Some kinds of air pollution are only slightly unhealthy, while some other kinds are incredibly toxic. But the kind of air pollution that should be of interest to you, the kind of air pollution that is concentrated in and around human settlements, the kind of air pollution that is concentrated at the altitudes where humans come in contact with the air in the first place, and the kind of air pollution that is the most hazardous to human health and well-being, that kind of air pollution is overwhelmingly produced by combustion activities. Pretty much all burning produces air pollution, and in this video I'm going to explain how the pollutants come into existence, which fuel produces which pollutants and how that works. I'm also going to cover how most emissions are actually avoided or mitigated, because there has been a lot of progress made since combustion first became a thing, and in the process you're also going to see which of these are still a problem. I'm probably even going to cover your favorite fuel, the one that you think is so squeaky clean or natural, and I'm going to tell you why even it is bad. But that being said, hello YouTube, I'm Michael Size, and hydrogen seems like the most squeaky clean fuel you can possibly burn, and honestly it probably is. If you remember how chemical reactions work, you remember that chemical reactions aren't able to modify the atoms involved in the reaction. They're only able to rearrange the atoms into new molecules. The atoms that go into a hydrogen flame are just hydrogen and oxygen, and these elements alone aren't really able to form any weird molecules except water, especially in the context of combustion, where everything heavily tends towards smaller, simpler, more stable molecules. So even if you have incomplete combustion of hydrogen, that simply means that you're going to be releasing unburnt hydrogen, which isn't toxic or anything, and it isn't even a greenhouse gas, so where's the air pollution? The answer here is nitrogen oxides. In practice, fuels are never burnt with pure oxygen. In fact, that would be challenging to do even if you had a source of pure oxygen. But as it stands, the only source of free oxygen is air itself, which is a mixture of gases composed of about 80% nitrogen. The N2 molecule is typically very stable, but when heated to the temperature of pretty much any fire, it can actually participate in chemical reactions, and it reacts with oxygen to form nitrogen oxides, collectively known as NOx. The NOx typically produced by combustion activities is composed of about 90% nitrogen monoxide and 10% nitrogen dioxide, and it's honestly pretty incredible how complex the pollution from just these two molecules turns out to be. To start off, the nitrogen oxides are acidic irritants in and of themselves, but you'll see that that's actually just the start of the story. Once in the atmosphere, these gases interact with sunlight, which on the one hand can lead to the production of ozone, and on the other hand can lead to the production of nitric acid. The nitric acid can also be produced without sunlight more slowly, but whichever way it's made, nitric acid in the atmosphere leads to acid rain, and in some cases it can even be the primary cause of acid rain. Most of the ozone produced this way will get reabsorbed by the same chemicals, completing a sort of cycle. But if the nitrogen oxides encounter volatile organic compounds or VOCs in the atmosphere, these two can react with each other instead and produce smog. Smog is in itself an irritant, and some of its components can even be poisonous or carcinogenic. But it also makes the sky look nasty, which also counts as air pollution. The formation of smog is going to deplete the nitrogen oxides, which is going to break the previous cycle of reactions and lead to the accumulation of ozone. When ozone exists up in the stratosphere, it protects us against excessive UV radiation, but when ozone is down at the ground level, called ground level ozone, it becomes an air pollutant. Ozone is a very aggressive oxidizer, and it's particularly hungry for things like rubber, paper, textiles, and human flesh. Producing NOx is fairly inevitable if you're going to burn anything. So for the purposes of reducing air pollution, the task comes down to destroying it or capturing it before you release the flue gases into the atmosphere. Capturing NOx is possible, but it's kind of difficult and it doesn't really work as well as it does for other pollutants. Thankfully though, unlike with most other pollutants, NOx can be easily destroyed by a catalytic process into the nitrogen and oxygen from which it came, rendering it harmless. Now to be precise, while direct catalytic destruction of nitrogen monoxide is possible, and direct destruction of nitrogen dioxide might be possible, in practice these options aren't very attractive. So instead of direct destruction, catalytic converters also need to use a second reactant. In car exhaust, the second reactant is usually carbon monoxide or even unburnt hydrocarbons, which can be introduced into the exhaust gases by the engine simply by running the engine with a mixture of fuel that's very slightly above stoichiometric, colloquially known as running rich. But if you were burning hydrogen, you would need to introduce your own reactant, usually ammonia or urea. This method actually turns out to be necessary in a few other cases, not just for hydrogen fires, and in fact its use is rather widespread. This is the reason why semi-trucks and agricultural vehicles usually have a small urea tank right next to the fuel tank. As I said, nitrogen oxides are going to be produced by any fire, even if it doesn't have nitrogen in the molecule. This kind of NOx is called thermal NOx, and if the fuel did contain nitrogen in the molecule, such as if you are burning ammonia for instance, that would introduce a new mechanism for NOx production called fuel NOx. As we add more diverse chemicals to the fuel molecule, the pollution only gets more interesting, and the logical next fuel to look at is of course methane. Methane has a carbon atom, and carbon content is usually what opens the door to literally all of organic chemistry. But methane is so saturated with hydrogen that it really doesn't get a chance to do a lot of interesting chemistry. It probably can produce some non-zero amounts of stuff like soot and methanol under some circumstances, but from a normal methane flame, the only air pollutants that you're going to get in any serious quantities are going to be carbon monoxide, methane itself, and of course the NOx that all burning produces. Carbon monoxide is a poison, and methane, while not a pollutant itself, it's still one of the VOCs that can react with nitrogen oxides to produce smog and ozone, so we should probably do something to avoid this. There are approximately 2 ways to prevent these chemicals from making it into the atmosphere. The second one is to use a catalytic process again in order to destroy the pollutants that do get produced, and the first one is to not produce the pollutants in the first place. Carbon monoxide is a flammable gaseous fuel just like methane is, so it all comes down to ensuring complete combustion, which in practice means making sure that the fuel is thoroughly mixed with an excess of oxygen and making sure that the mixture gets hot enough and stays hot for long enough. I believe the technical terms are high temperature and long residence times. And I want to point out that methane should not be confused with natural gas, because while natural gas is in fact mostly methane and can even be over 99% methane, it's also usually contaminated with a few other fuels, which tend to have worse air pollution and greenhouse gas profiles than pure methane would have. So you should always assume natural gas to be slightly more polluting. If you remember my last video about electrically heated water faucets, in it I touched on all sorts of benefits, including life quality and lower greenhouse gas emissions. But what I didn't touch on are the benefits of lower air pollution. And the advantages here are even bigger than they seem at first glance. Not only because I'm not running the gas-fired tankless water heater as much, but also because I'm not running it as often. The flame is particularly dirty during startup and shutdown, and using it for hot water at the sinks probably means something like 50 startup events per day compared to 2 or 3 for the shower. And this is air pollution that's produced in my neighborhood, in my yard in fact. So think about how that compares to the power plant that's supplying my electric faucet, which, even if it was equally as dirty as the combi boiler, which it isn't, it's still 35 kilometers away from the city rather than literally inside the city. But I digress. The real fun in this video begins with larger hydrocarbons, and to understand their combustion, you first need to understand pyrolysis. Basically, when you heat up a molecule, there will always be a certain temperature at which the molecule starts to spontaneously break apart into smaller molecules. Breaking molecules using heat is called pyrolysis, and for most organic molecules, pyrolysis can occur at temperatures which most fires can produce easily. An example of pyrolysis is actually caramelization, and in fact a large part of cooking could be classified as pyrolysis, especially burnt toast, so you should be somewhat familiar with the process already. But in the context of a fire, pyrolysis is what ultimately produces the smoke that usually comes before the fire does. Smoke is usually made of aerosolized products of pyrolysis. It isn't a gas per se, but it looks a lot like a gas, it moves a lot like a gas, and it burns a lot like a gas. In fact, this is how most solid fuels actually burn. The solid pyrolyzes and turns into smoke, the smoke burns like a gas above the solid fuel, and the flame radiates heat back onto the fuel, driving further pyrolysis. This is why the flame is above the fuel, as opposed to being on the fuel, and this is also why that old trick works, where you can light just the smoke of a candle and the flame will travel down to the candle. On a chemical level, pyrolysis seems like it's simply breaking molecules into chunks of themselves, but if you look at it while actually paying attention, you'll notice that it can't actually be that simple, because it would leave unoccupied bonds where the connection used to be without enough hydrogen atoms in the mixture to occupy them. So in a practical sense, the products of pyrolysis aren't only fragments of the original molecule, but also all sorts of new molecules. For example, if you look at the pyrolysis of polyethylene, which is effectively just a super long alkane, a super simple saturated acyclic hydrocarbon, under pyrolysis it can produce everything from olefins to cycloalkanes to even benzene and all sorts of other aromatics. Many of those smaller random hydrocarbons are some sort of toxic. Butane, for instance, can damage the myelin sheath of your neurons, and benzene is famously carcinogenic. Larger products of pyrolysis may take the shape of solid or liquid particles, or may clump together into bigger particles which, when aerosolized, are known as particulate matter. These particles come in many sizes, and they are usually categorized by their diameter, measured in micrometers, and that's how you get PM10 and PM2.5. All of these particles are air pollutants, but not all of them are equally dangerous. They can differ in chemical makeup and they can certainly differ in physical size, and size actually makes a huge difference here. While larger particles like those in the PM10 category usually settle in the upper respiratory tract, from where you can maybe eventually cough them out, the finer particles like PM2.5 can travel all the way deep down inside your lungs, where they might settle permanently, literally permanently, or may even enter the bloodstream and contribute to heart disease. I'm gonna bring up electric vehicles to illustrate these differences. An argument is sometimes made that electric vehicles being 20% heavier lift up more road dust, which constitutes air pollution. And strictly speaking, this is probably true, but we also know that dust from the road is made up of fairly large particles, it's made of fairly benign chemicals, and it's already subject to aerosolization by wind anyway. At the same time, electric cars avoid 100% of tailpipe emissions, which are known to be particularly small, in fact having their own category as PM0.1 ultrafine particles, and are also known to often carry known carcinogens, such as polycyclic aromatic hydrocarbons. Additionally, electric cars use regenerative braking for everything except emergency situations, which means they also get rid of nearly 100% of brake dust, which is suspected to be equally as bad as tailpipe particles. Clearly, all particles are not created equal, but what they do have in common is that they are all aerosols. And this physical nature means that all of them can be captured by filtration systems. But going back to smoke and pyrolysis specifically, we know that the products of fuel pyrolysis are pretty much always flammable fuels. Getting them to burn is oftentimes a lot simpler, cheaper, and lower maintenance than clogging up your filters with them. Once again, you want to keep combustion as complete as possible, and once again the ways to do that are thorough mixing, appropriate oxygen access, high temperatures, and long residence times. The feasibility of employing each of these methods varies between different use cases. Stationary facilities with near constant power output, such as baseload power plants or garbage incinerators, have big advantages in this sense. Not only because they get to focus on the combustion part of the task above anything else, but also because their stationary nature essentially eliminates the weight and volume constraints both for the combustion chamber as well as for the emissions cleaning system. Facilities such as peaker power plants have a bit of a harder time with it, because to some extent they have to focus on serving the real-time power demand, which affects both the combustion efficiency as well as the effectiveness of the exhaust cleaning system. They would be best replaced with batteries or even hydropower peakers if your grid is blessed with enough hydropower, but nevertheless they are still fairly clean. The part where combustion gets very dirty is in things like combustion vehicles. A vehicle engine has the primary task of satisfying the real-time power demands of the gas pedal, so it doesn't get the luxury of focusing on combustion quality. Combustion vehicles are forced to rely almost entirely on cleaning up the exhaust gases after the combustion, but because of the size and weight constraints of being a vehicle as opposed to being a building, their exhaust systems aren't all that sophisticated either. And this is yet another overlooked advantage of electric vehicles. Because everyone only focuses on the climate aspect, but even if you charge the electric car on electricity generated from a coal power plant, in which case your climate impact stays roughly unchanged, the coal power plant might still produce air pollution. But the power plant can be placed 100 miles away from the city, where the pollution has plenty of space to dissipate. Now, there are design decisions that you can apply to improve the combustion inside a combustion engine, but what if you applied none of them? And I also told you that there are ways to clean the emissions of a combustion engine, but what if you used none of them? Well, my friends, if you own any combustion engine power tools, I want you to listen to this next part very carefully, because a chainsaw burning 1 liter of gasoline produces the same amount of NOx as a brand new EU compliant car driving 1,000 kilometers. You can fact check this by looking at the emission standards for each of them, but this really shouldn't be surprising at all. These devices run 2-stroke engines and spill the exhaust directly in your face. And it's being done like this simply because there is no way to fit emissions control systems onto something that's handheld. And I know battery power tools are fairly expensive, but I also know so many people who do stuff like yard work or garden work or cutting up logs for firewood well within the range of a suitable electrical outlet. If you're among them, do yourself a favor and at least get yourself some corded electric power tools, along with a 50-meter extension cord, and stop choking on fumes. And if you have to choke on fumes, at least get yourself appropriate protective equipment. But moving on from just boring carbon and hydrogen, let's see what happens when you add sulfur to the fire. Handling sulfur is a bit different from what we've seen so far. Sulfur is a flammable fuel, so if it's a part of your fuel molecule or mixed separately within your fuel, you very well might be able to achieve complete combustion of the sulfur. But the problem is that the product of that complete combustion is in itself an air pollutant. Once released, sulfur dioxide reacts with water in the atmosphere and forms sulfuric acid, and sulfur emissions from coal combustion is how acid rain became such a large problem back in the day. So complete combustion doesn't help, and you also can't filter the sulfur dioxide because it's a gas, it simply passes through filters. Catalytic processes aren't going to help because there isn't any target molecule that you can hope to transform the sulfur dioxide into. Pure sulfur molecules are solids, so even if you could make them, they would deposit on your catalyst and render it useless. And any different gases that you might be able to turn the sulfur dioxide into are still the pollutants that you're trying to avoid in the first place. The way to deal with sulfur dioxide, as it turns out, is to find a chemical that can react with the gaseous sulfur dioxide and turn it into a solid sulfur compound, or even a liquid sulfur compound, which would be easier to separate from the rest of the gas stream. There are multiple options for this, but the preferred reactant is usually lime or limestone. Getting a gas from a fast-moving gas stream to react with a solid isn't a trivial matter, but the best way to do it in this context is to use a wet scrubber that essentially rains a water and limestone solution over the flue gases and collects the wastewater at the bottom. The wastewater contains the reacted limestone, which has now turned into calcium sulfate, otherwise known as gypsum, and one reason why limestone is preferred as a reactant in this process is that the resulting gypsum is mostly insoluble in water, which makes it easy to separate out of the wastewater. Gypsum is a commercially valuable product, and in fact around 30% of the drywall on the market is produced by flue gas desulfurization. Producing it like this isn't always a profitable endeavor, but it can definitely help offset some of the cost of the scrubbing equipment. Large-scale implementation of this technology is how acid rain eventually ceased to be a problem. And just like acid rain, a majority of these pollutants are as harmful to plants as they are to humans and animals. Cleaning up the emissions from cars and power plants is responsible for about 20% of US agricultural yield increase over the past 2 decades. Of course, cars don't have sulfur scrubbers, but the sulfur now gets removed at the oil refinery, protecting your engine as a bonus benefit. Coal is loaded with sulfur partly for the same reason why coal is loaded with literally everything. Because coal used to be literally the ground at some point, and it hasn't gone through any gasification or liquefaction process, so all of the dust and dirt that once settled on the ground from wind and water are still exactly where they settled. When you burn coal, you're taking an accumulation of carbon that has dust layered inside of it, you're turning the carbon into gaseous CO2 which escapes out the smokestack, and what you're left with is just the dust layers, except now they're concentrated, and that's what makes up coal ash for the most part. This is one of the reasons why ash exists, contamination of the fuel with solids that aren't going to burn and end up as ash. But it isn't the only reason. Lots of other chemical elements might very well participate in combustion, but the oxides they form are solid chemicals. And this includes a lot of the elements that biology makes use of. Sodium, potassium, calcium, phosphorus, these are all examples of chemicals that do exist in biological life, including in wood for instance, and which after a fire will be left mostly in the form of their respective oxides, which are solid chemicals. And for the most part, this is what wood ash is made of. Ash is almost invariably a solid, but as we've already seen with fine particles, just because it's a solid, that doesn't mean it can't become an air pollutant. If the ash settles at the bottom of the incinerator like a good boy, that's called bottom ash, but if the ash decides to follow the flue gas currents up and out the smokestack, that is called fly ash, and it's yet another air pollutant. Fly ash is mostly bad because it's made up of irritants, but it can also contain dangerous toxins and carcinogens, usually in the form of heavy metals. Fly ash is a lot larger than what we've previously referred to as particulate matter. You can maybe think of it as PM100. And it also isn't flammable at all, so in order to remove the fly ash from the flue gases, you don't get to burn it, this time you actually have to capture it. There are approximately 3 technologies that can be used for this. You can use traditional filters, but that means you're constrained to lower temperatures and you also get a pretty large pressure drop. You can use a wet scrubber, which gets you the cleanest exhaust but generates a lot of wastewater, or you can use an electrostatic precipitator, which is not super efficient but it has the lowest externalities. In practice, the most effective method is usually a combination of those. Something like electrostatic first, to capture the bulk of it cheaply, and a wet scrubber second, to clean up anything that got missed by the first method. Heavy metals aren't usually useful to biology, and in fact they're usually poisonous to most of biology. But despite this, if heavy metals are present in soil or water, plants and animals can accumulate them, which means that even your all-natural organic firewood can still release fly ash that contains things like lead and mercury. Most of the heavy metals in the fly ash will exist in a solid form, so filtration works just fine. Filtration also works for aerosolized liquids, but what it doesn't work for is gases, and one particularly problematic heavy metal is therefore gaseous mercury. The main way to capture mercury is to get it stuck inside of something that's called a sorbent, most typically a particle of activated carbon. The carbon particle is a solid, and that means that it can later be captured like a solid. You can insert the activated carbon directly into the gas stream before it reaches the filters, or alternatively you can put the activated carbon into the scrubbing liquor of the wet scrubber. Heavy metals are very bad, and they're definitely some of the scariest air pollutants. But what if I told you that you can have compounds that are just as harmful and terrifying as heavy metals are, but which can be made without using any heavy metals at all? This class of pollutants is usually referred to as dioxins, but don't get confused by the name. Dioxins is just what people call them, and it is what I'll be calling them, but it's not necessarily what they actually are. The substances that I'm calling dioxins in this context are polychlorinated biphenyls, polybrominated biphenyls, polychlorinated dibenzodioxins, polychlorinated dibenzofurans, polybrominated dibenzodioxins, and polybrominated dibenzofurans. So in terms of what they actually are, there you go, it's these classes of chemicals. But what exactly makes these chemicals so bad? Well, basically it's the halogens, sort of. Halogens are a group of chemical elements that includes fluorine, chlorine, bromine, and iodine. And it turns out that when you add halogens to an organic molecule, sometimes you get a molecule that is super stable, by which I mean that it doesn't get destroyed out there in nature in the same way that most pollutants do. So instead of being a regular pollutant, it becomes a persistent pollutant, and in the case of dioxins, these are organic molecules, which means that they are persistent organic pollutants, or POPs. Not all POPs are dioxins, of course, but dioxins are POPs, and the halogens usually involved here are chlorine and bromine. In terms of toxicity, dioxins are really bad. They are persistent like heavy metals, they are toxic and or carcinogenic like heavy metals, they bioaccumulate like heavy metals, and as a result, despite the world taking significant measures to curb dioxin production, these chemicals have become so widespread that they're nearly inevitable.
They're present in soils and food supplies pretty much everywhere on the planet.
In terms of defending ourselves against them, as a long-term solution, we really should stop releasing them. So how do we do that? Obviously, in order for a fire to make these compounds at all, the fuel that you're burning needs to have halogens inside it to begin with. Biological fuels do contain halogens, albeit in very small amounts, and it turns out that even ionic compounds such as sodium chloride, table salt, can still end up participating in chemical reactions within the chaos of combustion. So while your good old wood-burning fireplace can in fact produce non-zero amounts of dioxins, the focus really should be on chlorinated plastics, and the most common among those is PVC, whose molecule is literally over 50% chlorine by mass. When PVC burns, two main things can happen. Under incomplete combustion, PVC can produce dioxins directly, along with a bunch of other compounds, while under complete combustion, it produces hydrogen chloride. All halogens will produce their respective hydrogen halides, and these chemicals are acidic gases, which of course means that they can contribute to acid rain. But additionally, in a certain temperature window, hydrogen halides can react with soot in the flue gases to form brand new dioxins. I believe the technical term is de novo synthesis. So this means that you can destroy all of your dioxins in the burn chamber by achieving complete combustion, burning them all the way down to water, CO2 and the hydrogen halide, and then somewhere in the boiler area, the halide makes new dioxins right back at you. To deal with dioxins, of course, you want to start with complete combustion as usual, but now it also matters that you cool the flue gases as rapidly as possible, especially as they pass through the 400C to 250C window in order to minimize de novo dioxins. Once cooled, the dioxins in the flue gases can be captured in activated carbon, just like the mercury can, and once again this works with dry sorbent injection as well as with sorbent in the scrubbing liquor. As for the hydrogen halides, they're all very soluble in water, so the first wet scrubber that the exhaust passes through will almost inevitably capture them. From there, they can be neutralized with an inexpensive base, such that they form an insoluble salt which can be safely landfilled. But now that you know so much about air pollution and flue gas cleaning, I want to tie this whole video together with an example of a possible all-encompassing flue gas cleaning installation, such as what you might see on a municipal solid waste incinerator, which has to deal with pretty much every pollutant imaginable. Now, these setups can vary a lot. Not all of the flue gas cleaning systems are going to look exactly like what I'm about to describe here. But I'm pretty confident that this is going to be a realistic system, so here goes. The first task is always to ensure complete combustion, because you don't want to be filtering anything that you could have burnt instead. After that, you want to cool the flue gases rapidly, especially as they go through the temperature window of de novo dioxin synthesis, and then the actual cleaning starts. The first cleaning step will be the electrostatic precipitator, which captures the vast majority of fly ash and particulate matter. Now at this point, some of the most modern facilities will actually put a selective catalytic reduction system immediately after the precipitator in order to take advantage of the high flue gas temperatures, which make the catalyst more efficient. So if that's the case, most of the NOx in the flue gases will be removed at this point, along with some of the dioxins. The next step is the first of the wet scrubbers. This first one will almost inevitably produce a highly mixed wastewater, because it will almost inevitably capture the hydrogen halides as well as almost inevitably capture the remaining particulate matter. This means that now is probably the right time to add the sorbent to the scrubbing liquor in order to capture the mercury and dioxins, such that you can have all of these contaminants concentrated in only the first wastewater. The NOx and the sulfur dioxide aren't very soluble, so the vast majority of these will move on to the second wet scrubber. It isn't technically necessary to capture the sulfur in a whole separate scrubber. You could just as easily add the limestone to the first scrubber, but there are at least two reasons why it's desirable to do it like this. Firstly, contaminating the gypsum with the sludge from the previous scrubber would make the whole mixture hopelessly contaminated, which would mean that you're giving up on the gypsum revenue. And secondly, it would bulk up the sludge from the first scrubber, which would mean that you have to pay extra gate fees at the hazardous waste landfill. In any case, the sulfur is now gone, and in this particular system, our job is done. But if we hadn't added the catalytic reduction at the beginning of the system, the very end here would be the other typical place to put it in. The flue gases are now well below the legal contamination limits, and they can be safely released to the environment. With today's focus on climate change, I find that a lot of people have lost track of classical air pollution. A lot of the information that I've shared today is oftentimes pretty shocking the first time you hear it. I would have honestly never guessed how bad dioxins are, or that tailpipe particles can cause heart disease, or that chainsaws do it thousands of times more concentrated, and I certainly would have never guessed that coal power plants reduce crop yields around them. It isn't difficult to see how a lack of a good understanding of air pollution can lead you to have some pretty uninformed opinions about what is a threat and what isn't a threat to our health and environment. And I hope I've played my part in improving this. I hope this video will make a good reference point. Thank you all for watching, and the subscribe button is just above the like button.